picture this. You're a top-tier surgeon about to perform a highly complex, literally life-or-death procedure. Now, what if you had a tool right there that could analyze every single past case, every tiny variable, and accurately predict the outcome before you even make that first incision? Well, let me tell you, that's not sci-fi anymore. It is the absolute frontier of modern healthcare right now. With patient demand just skyrocketing and resources stretched incredibly thin, relying on intuition, yeah, that just doesn't cut it. So medical professionals are leaning hard into advanced machine learning. They're using these techniques to analyze past cases and drive predictive operational efficiency, which radically improves how they make decisions on the fly. So, welcome to this explainer. Today, we are unpacking the mechanics of machine learning techniques in predictive analytics. Okay, let's dive into this and explore exactly how these models turn massive data sets into literal, life-saving operational forecasts. Here's a quick look at our roadmap. We've got 1. The power of prediction. 2. Battle of the algorithms. 3. Inside artificial neural networks. 4. Types of neural networks. And finally, 5. Support vector machines explained. That way you know exactly how we're going to demystify these algorithms. All right, starting off with section 1, the power of prediction. As we just touched on, predicting outcomes in complex scenarios like medicine, it isn't just some neat academic exercise. It is a critical operational need. Moving right along to section 2, battle of the algorithms. Let's transition into a really high-stakes contest and see exactly how different predictive models perform when they are actually put to the test. So, researchers took a bunch of pre-processed data and partitioned it out to train, calibrate, and then test 4 distinct predictive models. Who are the contenders here? Well, we've got artificial neural networks, support vector machines, and 2 decision tree algorithms known as C5 and CART. Now, to make this a fair fight, they all ingested the exact same data and underwent identical sensitivity analysis. It's kind of like a scientific cage match. And when the dust finally settled, the results were absolutely definitive. Looking across accuracy, sensitivity, and specificity, the support vector machine, the SVM, secured a commanding knockout victory. I mean, look at that overall accuracy of almost 88%. It vastly outperformed the C5 decision tree, the artificial neural network, and the CART model. So SVM is our clear champion here. But why? Well, to understand that, let's look at section 3, inside artificial neural networks. Let's pull back the curtain a bit and see how these models actually process information in the first place, starting with the classic artificial neural network. As you likely know, human brain cells process information using a central body called the soma. They receive incoming signals through these branch-like structures called dendrites, and then they fire signals down the axon to the next neuron across a gap called a synapse. It is a beautifully complex organic chain reaction. And this brilliantly illustrates exactly how the artificial model works, because it maps directly to that biology. We just replace the biological cell with a mathematical processing element. Those incoming signals, those are our inputs, the artificial dendrites bringing in data. But, not all data is equally important, right? So each input is assigned a weight, which acts just like that biological synapse. If the summation function's threshold is met, it fires through a transfer function to create our output, which is our artificial axon. So the biological components directly inspire the artificial ones. It's a straight bridge from biology to silicon. But here is the absolutely critical insight. Your human brain processes things relatively slowly, but it uses billions of neurons to do it. An artificial neural network, on the other hand, operates with blinding mathematical speed, but it typically only utilizes dozens to maybe hundreds of thousands of nodes. It is a fundamental trade-off of biological scale for raw computational speed. Next up, section 4. Types of neural networks. Because, as it turns out, an ANN's architecture is strictly driven by the specific task it needs to tackle, like classification or clustering. That biological inspiration leads to some really different architectures. For instance, in a standard feed-forward network, the signals just flow linearly, straight from input to output. Nice and simple. Conversely, a recurrent neural network is a lot more dynamic. The nodes actually have connections that loop back on themselves. This gives the network a sort of internal memory, which makes it absolutely perfect for analyzing sequential data over time. And the architectural variety is just vast. Take self-organizing maps, pioneered by Teuvo Kohonen. They are incredibly useful for clustering data when you don't even have pre-labeled categories. Meanwhile, you've got things like hot field networks, which feature a highly interconnected web where literally every single node connects to every other node. Those are specifically designed to solve really complex computational optimization problems. All right, moving to our final section. Section 5, Support Vector Machines Explained. Let's pivot back to our scoreboard winner and see how SVMs map input variables mathematically to pull off that superior prediction. Remember our champion, the support vector machine? It won because of how it fundamentally views data. Real-world health records? They're messy, they're nonlinear. You can't just draw a simple straight line through them. Enter the kernel trick. It's essentially a mathematical life hack. It takes that tangled nest of nonlinear relationships and transforms it into a higher dimensional space where suddenly they can be separated by a nice, clean, straight line. So it separates this data using what's called a hyperplane, basically a spatial geometric boundary. But it's super clever. It constructs two parallel hyperplanes, and its goal is to maximize the geometric distance, or the margin, between them. The wider the gap, the more confident the prediction is. And amazingly, the complexity of this whole operation relies strictly on the data points sitting right on the edge of that margin. We call those the support vectors, rather than getting bogged down by the massive size of the overall data set. Bringing this narrative full circle back to real-world stakes, these complex models are actively saving lives far beyond hospital walls. Take the inherently hazardous mining industry. Down there, neural networks are constantly analyzing environmental data and structural sensors. By predicting potential failures before they even happen, operators can evacuate personnel and literally prevent fatal catastrophes. And we see similar massive applications over in the electric power industry. Power generators utilize predictive modeling to forecast emissions and tightly optimize their fuel consumption. It just goes to show that these algorithms are truly foundational to managing and optimizing our modern, highly complex world. By mirroring biological brains or using clever mathematical life hacks to draw boundaries in incredibly complex data, these models are constantly learning from the past to secure our future. So, as these machine learning techniques become even faster and fiercely accurate, you gotta wonder, what impossible global challenge will they solve next?